that one was quite big. There was a lot to do in that, but I think the next one is kind of short. Okay. Next topic. Come on. Rocket science. Our full title is Conservation of Momentum, or Rocket Science, what I'd like to call it, because that's usually how it is in the exam.
In the elevator, if we are in the air, like the sides, we take the sides and we are, my weight is up, fall down.
For the elevator?
I'm gonna hurt myself, or?
Like I said, if you're in a fallen elevator, the best thing is to lie on the ground. No matter what's going to happen, the elevator is going to hit the ground. You can jump up, you can hold onto the walls, it doesn't matter. You're going to be in an elevator that's going to hit the ground. That's the situation. So the best thing to do is to be in a position that will break the least of your bones. Okay? So the position that will break the least of your bones is probably lying on the ground. Yeah. You just have to accept this. You're in a fallen elevator, some bones are going to be broken, you get into a position that will break the least of your bones.
So you'll go to which bones, which area would be the most?
I think if you're lying on the ground, it would probably be pretty random. But if you're standing, you'll definitely break your leg bones. Okay, but if you're lying on the ground, maybe, you break a rib or one of your leg bones or something. Probably not your leg bones. Probably be your ribs, I'd say. Yeah. Ribs are okay to break because ribs repair pretty nicely. It's your leg bones that if you break them, it can be a bit messy to repair. Ribs do okay when they're broken.
Once I had broke my hand.
Wrist?
No, this one.
Oh, here. Oh, okay, yeah. Painful?
No, yes, it's painful. I fell
Same here.
when I was.
You too? Oh, yeah.
Training horse riding.
Oh, you fell off?
Yes.
Oh, yeah. And you put your hand on the ground when you landed?
No, because I'm still beginner.
You're still a beginner, yeah?
Yes. Now I know how to jump.
Oh, you were trying to jump with the horse?
No.
How did you break your arm though? Did you fall off the horse?
No, I didn't. I do not remember because
You must remember.
No, I was so when I fell, maybe I fell.
Yeah, okay, you fell and maybe you landed like this, okay. You were very small then. Yeah, you don't even remember.
He knows everything but he don't remember.
Huh?
He knows everything but he don't remember.
Yeah, well maybe it was so traumatic, we blanked it out.
I won't forget this one.
Yeah.
No.
You'll never forget this. Okay, yeah. Alright, so I said earlier today that Newton's second law, the way we said it was, what was Newton's second law? Force equals mass multiplied acceleration. That's one way to state it, but there is another way to state it. Another way to state Newton's second law is F equals delta P over delta T. Now, what are those terms?
T is time.
So T is time. Momentum. Which I have to explain what momentum is. So delta T is the change in momentum and delta T is the time. So we need to explain what momentum is. Does anyone know momentum?
We took it, but I think.
Do you remember?
Momentum is the product, I think, of force and that is equal to PV. MV,
that's it, yeah. Momentum is just the product of mass and velocity. So that is, momentum is just mv. So what would be the units for momentum?
M is mass and velocity.
So the units?
Unit mass per kg per meter second. Kg per second. Kg
Where
meter per
are
second.
definitely,
Meter per second.
kilogram meters per second.
Yeah.
Yes. Okay. Okay. So what I'm going to do is I'm going to prove that in fact you can get the same result that F equals ma. Okay. Can I continue? No.
Yeah.
We're waiting for a couple of people. Okay. Andy?
Yeah.
Which part are you writing down? You got it? Okay. So, watch this now. Let's say we have an object and it starts at velocity u and I apply some force and it accelerates. So its velocity is now v. So you know acceleration is when the velocity changes. So another way to say Newton's law is F equals change in momentum over change in time. And I'm going to prove that this is the same answer as F equals ma. So change in momentum, that means the momentum at the end, that means the momentum at the end minus the momentum at the start. That's what this delta means. It means the change, the difference. And the time, well, what's the time at the start? That's 0 seconds. And the time at the end, that's t seconds. So what's the change in the time? Well, it's just t. Yeah. Okay, what's the formula for momentum? mv. So what's the velocity at the end? It's v. And what's the velocity at the start? u. Over t. So I can take the m out, and I'm left with v minus u over t. But you need to remember that we said v equals u plus at, so v minus u over t is equal to a. So if you put that in there, you get that this equals ma. So therefore, F equals ma. So although it's a different formula, you can prove that it makes the same result. So now we have two ways for Newton's second law. We can say force is the change in momentum over the time, or force is the mass multiplied by acceleration. Do you really go to the bathroom, or do you have a quick smoke?
I swear that I went to the bathroom, but I smoked so much. I live in A block, so it's a long way. But I did go to the bathroom.
Okay, fine.
I swear.
But you had a cigarette on the way.
On the
Okay,
way.
fine. Man, you must be desperate now for a cigarette if you...
Yeah, like, I really need it.
You really needed it, okay.
I smoke a lot.
It seems like it, yeah. If you can't wait another 20 minutes.
No, I just took advantage of it.
Oh, okay, I see, alright.
2 in 1.
Yes. Okay, do we have this now?
Yes.
What if I did this while I was in the elevator and de-accelerated at
No.
19?
Oh my goodness, you would need super strong legs to do that.
Yeah, but technically,
If you were strong enough to do that, you'd be like Superman and you wouldn't be worried.
what if I had like a shoe that...
Like Super Mario shoes that make you jump really high.
No, like... stuff, you know, like...
I think this is getting a bit
It's
ridiculous now.
gonna rip my legs.
Yeah. Maybe you should just avoid elevators if you're so worried about it. Alright, continuing. Right. So we proved that this is the same formula as F equals ma. So why bother with this formula if F equals ma works? Like, why would we need two formulas if we have one that already works? Well, the reason is this formula is very convenient to use when the time the force is being applied to is very small. So usually what happens is we use this version here, usually when the t is really small. This is the normal situation, okay? Sometimes it's difficult to calculate the acceleration when the t is really small. This is sometimes difficult to do. Sometimes it's easier to calculate the u and the v, okay? Also, sometimes we want to know what the t is, and then if we want to know what the t is, it's easier to use this formula if we know the f and the delta p. Also, it's worth saying that the delta p, this part of the formula, the delta p, actually has a special name. We call this delta p the impulse. It's another name for the change in the momentum. That is, the I is also called delta p. So if I asked you what is the impulse, that is the same as asking what is the change in the momentum, which is the same as asking what is the difference between mv and mu. Okay, you have this box. Impulse is the change in momentum. Yeah? Okay, continue. So now that we have some definitions and examples, let's look at, formulas, let's look at an example. So before we write this down, let's read it. So again, we're looking at the example we had last week. So do you remember that we had the car that crashes into the wall, and while the crash is happening,
about the video?
The video, yeah, the wall is providing a reaction force that is stopping the car. And you remember that the calculation, was a little bit difficult. In this one, what we have is the same car and the same speed, and we want to know what is the impulse. So what is the impulse? That is the change in momentum. Yeah. So, and you know what? I think you might be able to do this yourself. It's not too difficult. Why don't you read it and try to do this one, okay? I'm asking for the impulse. Remember, impulse is the change in momentum. And what's the formula for momentum? mv. Do you know the m?
Yeah.
And do you know the v's?
Yeah.
Yeah, so try it. I don't think you can do it. You can draw it. You don't have to write it down if you want to draw it.
Okay.
V equals
I is delta p. I is the change in momentum. Yes, yeah. So let's have a look here. Right, so here is the wall, and here's the car. So at the beginning, the u is 20 meters per second, but at the end, yeah, the v is 0 meters per second, and the mass is always, what do we say, 1200 kilograms. Yeah? The impulse is the change in the momentum, which will be mv minus mu, which will be 20 times 1200 minus 0, which is 24,000, and the unit is kilogram meters per second. Okay, so now the big question is, what does the impulse represent? If you were trying to explain what the impulse is, what would be is this a big number? Is this important to know?
It's showing the change in...
Yeah, it's showing a change in what exactly? The momentum. But why would we care about that?
Because of the velocity?
Yeah. And let me put it like this, okay? If you think about your formula, your F equals delta P over delta T.
Yeah.
And remember, the delta T is the time the force is being applied, so it's the contact time here. But that's not important right now. If this is getting bigger, then it means that the force is probably getting bigger as well. So in other words, the impulse is a way to It's something that when it's very large, it means something dramatic happened. If the impulse is very big, it means the momentum changed a lot. And the only way momentum can change a lot is if there's some drastic force that's changing it, you know. Like, for example, if the car was only going, let's say, 1 meter per second, then this number would be much smaller, and the crash would not be so bad. In other words, the impulse, if you want to think about it simply, is what hurts. If you ran into the wall and you suddenly came to rest, or if somebody punches you or whatever, it's the impulse that hurts. It's the change in the momentum that you experience is what causes the damage. Okay? So yes, if the force is very big, that will hurt. But if the time is very small, then even though the force is big, if the time is small, then it's not so bad. It's the impulse that hurts. It's the change in momentum that really is what does the damage. Okay? So if I was to punch you really hard, but I did it very quick, maybe it's not so bad. But if I was to take you and then change your momentum by throwing you, that would hurt a lot more, you know. And it would hurt a lot more when you hit the ground, when your momentum suddenly becomes zero. Okay. So the reason we care about impulse is that it's what causes the damage, the hurt. Right, here is another example. A hammer hits a 100-gram nail with a force of 50 newtons, and the nail moves at 4 meters per second. How long was the force applied to the nail? So if you think about it, if you put the nail into the wood and you hit it, the time the force is in contact with the nail is quite small, because when you think about it, it's less than a second. It just goes bunk, like this. So, you know, like maybe 10 milliseconds. And so what we would like to know is what is the force. And the only thing that you know is, you know the force, is it the force? No, sorry, the time. We know the force of the hammer, we know how hard we hit the nail, and we know how fast the nail goes when it moves. So it goes 4 meters per second, let's say. So again, if you can just draw or write this down, and then I'll do it. Okay, so here's another example. Okay, let's have a look. It's 100 grams, there's a force of 50, and the velocity is 4. Okay, so, if we have a look here, right, here is our nail, and at the beginning the U is 0, of course, and then at the end, as it's after it's struck, it's moving at 4 meters per second, or I suppose minus if you want. Okay. So here, between here and here, the reason it moves is because there's a force of 50 newtons from the hammer, and we want to know what is the time the hammer is in contact with the nail for, the delta T, the contact time. So we can use our formula, F equals delta P over delta T. So a little rearranging, and we get delta T equals delta P over F. The F we know, it's 50, and the delta P is mv minus mu. But what's the U?
U is
0. So the delta T will be m, which will be 0.1, v, which is minus 4. It's going down, isn't it? Yeah. Oh, sorry, and my force is minus 50 going down. Yeah, and minus 50 here. So we get 0.4 divided by 50. Yeah, 0.1 times 4. Yeah. So we get 0.008, or in other words, 8 milliseconds. Not meter seconds, milliseconds. So quite a small amount of time. Yep. Okay, got that? Yes, continue?
No, one second.
No? Okay.
One second.
So do you see what I mean, that the other version of Newton's second law is very convenient when you need to work out times, especially? Yeah? Okay, continue? Right. Right, here's another example. Again, you can just draw or write down the key information. A 250-gram football is at rest. A football player kicks the ball and the ball moves away at a speed of 10 meters per second. Work out the impulse on the ball. Okay, so we just want to draw it and then I'll do it. Okay, did you get the key information? Well, there's not much. All that really is in the question is the ball is at rest. What's the mass of the ball? 0.25 kilograms. And then the ball is kicked and it moves away at 10 meters per second. And the first question is, what is the impulse? Well, what's the definition of impulse? It's the change in momentum, which will be mv minus mu, but in this case the u is 0, so it's just mv, which will be 0.25 times 10. So the answer is 2.5 kilogram meters per second. And then the second part is, if his foot touches the ball for 100 milliseconds, how much force did his foot provide? Okay, because you know when you kick the football, you're only in contact for a short time. So in the question I said 0.1 seconds.
Then we'll divide it by the second.
Yeah, well, so we have force equals delta P over delta T. So 2.5 divided by 0.1, and the answer is 25 newtons from his foot. Not so bad. Okay. Let's see what the next one's like. Ah, yes, okay. So there's actually one last thing to show you, I think. Right, so I need to move on just so I can finish. Yeah. So this is the biggest advantage to using this formula. Okay, the biggest advantage is that it allows you to calculate the force provided by rockets. Okay, so if you think about the hot gas coming out of the rocket, it has a mass. You see this gas here? Yeah. It has a mass, and it has a velocity. So if you know the mass and velocity of this gas, you can know the force upwards for the rocket. The gas was at rest. When the gas is in here, is it moving? No. But when it comes out, it's moving. So it has an impulse. And remember, when there's an impulse, there's a force. Because its momentum changes. So let's do a little bit of a calculation, and then one very quick example. So I'll run through this proof very quickly. Right, so here's our rocket, and here's our mass. That's a rocket. Here's our mass, and we'll say the mass is delta M. And at the beginning it's at rest, 0. Okay? But then when the mass comes out, like this, there's delta M. Is it at rest? No, it has a speed, which we'll call delta V. Now the reason I'm calling it delta M and delta V is because I'm doing this per second. Because each second mass comes out. Okay, so that M is not the total mass, it's how much comes out each second. Do you understand? It's like each second I picture mass coming out. Do you understand? Yes? Okay. So, what is the impulse? The impulse is the change in momentum, which will be mv minus 0. Actually, but because it's going down, it's a minus, so I'll say it's minus delta m delta v. But remember Newton's third law. For every action, there's a reaction. So the gas being fired out causes the rocket to go up by an equal amount. So then the impulse on the rocket will be delta m delta v. But what's the formula for force? Force equals impulse over time. But I just said, what is my unit of time? I'm looking at it per second. So the delta t is 1. So then you get this very, 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 very nice result. That the force from the rocket is equal to the mass per second of the gas that comes out, which I'm calling delta m, times the speed of the gas per second, how fast the gas comes out, which I'm calling delta v. So if you know how much gas comes out per second, and you know how fast it's going, then you know how much force the rocket has. So this is a very nice formula for calculating the up force on the rocket. So if you want, you can write this down, but from the video, please. I don't have time to look at this, because I want to give you an example with numbers. Okay? So, for example here, this is the mass of the rocket. This is how fast the gas is.
And this is the kilogram.
And this is the how much fuel there is. Now you might say, wait a second, this number is much bigger than this number, which is actually quite normal. When you think about a rocket, it's mostly gas, it's mostly fuel. Only a very small part of it on the top is actually rocket. Okay? So you can do it on your calculator. If this is how much gas comes out per second, that's a lot, and this is how fast it's coming out, what's the up force on the rocket? Well, we just have to multiply the speed of the gas and how much gas comes out per second. So it's 7,485 kilograms per second of gas.
What is it?
That's the bottom of the rocket. And the speed the gas comes out at is 4,462 meters per second. Multiplying the two, and I have my up force. What do you get? Probably a huge number, is it?
Yes, 33 million.
7,485 times 4,462. 333,98070 Newton. Is this okay? It's just multiplication of the two.
So we don't convert 7,485 kilograms per second. We just leave it like it is.
What do you mean convert?
It's fun.
Kilograms per second.
Yeah, that's what you want. You want to know how much mass per second is coming out. Yeah.
Okay.
Yeah. Okay? Yeah. By the way, if you were to multiply these units together, you would get kilogram meters per second squared, which earlier in the course we said was the same as a Newton.
Yeah.
So the units work.
Yeah.
And in fact, this was not important to the question. I just put that in as a distraction. All you really need to know is how much gas comes out per second and how fast it comes out. Right, oh, okay, this one's a bit difficult. Okay, so you know what? At the start in the next class, I'll do this, I'll continue with this example. But wait. I do want you to do some of these, the easy ones.
Okay, tell me just.
1 and 2. Do question 1 and 2, and then I'll continue. You can't do 3 and 4 yet, but you can do 1 and 2.
3 and 4?
No, I said you can. Well, I don't think you can do 3 and 4. You shouldn't be able to, but you can do 1 and 2, okay? I think what we'll do is I'll finish this lesson the next time, and we'll do 3 and 4 in class together, since they're a bit difficult. But don't forget, you also have the first homework, the reaction form,
Yeah.
okay? Alright, see you on Friday then.